All right, everyone. So welcome back to our second week. So we are going to transition now from talking about limits to probably one of the most common ways limits are used, and that is what is called the derivative. Okay, so back on the first day, we talked about what is called a secant line. So if we have 2 points on some curve P and Q aren't equal to C, then the line that connects P and Q is a secant line. And the slope of that secant line is given by the rise over the run, so change in y values divided by change in x values. And if we wanted, we could find the equation for this secant line. So we could find it with the point slope form for lines, which is y minus one of the y values is equal to the slope times x minus the corresponding x value. And this slope of secant line is called the average rate of change for the function f over the interval x1 to x2. Right, so we had these images of some secant lines. So here we're connecting the points 0, 0 and 2, 2. So a secant line between x equals 0, x equals 2. Then we have a secant line between x equals 1 half and x equals 2. And then we kept going and taking secant lines where the left point got closer and closer and closer to 2 until they were just touching. Okay, so then what we could do is we could go and take a limit as that left point gets closer and closer to the right point. So what we were effectively doing pictorially was we were taking the limit as the left point got closer and closer to 2. The other way that we could write this, and this is the more common way of writing it, is we're taking the limit as h goes to 0 of f of x0 plus h minus f of x0 all divided by h. So effectively what the second definition is saying is you're taking the limit between the 2 points is going to 0 as you go towards the point x0. And this is what we call the slope of the tangent line. So the tangent line we could think of as a line, or I guess a tangent line to a function at a point. It is the line that goes through the point in question and has the same slope as the function, and that's what we'll see going forward. And we call this limit at a particular point the derivative of f at x0, and written using this standard limit definition. Okay, so we can go about finding some examples of derivatives for our function at various points. So we'll start off by finding the derivative for minus x times x minus 3 at the point x equals 2, and then do the same kind of thing for x equals 3 halves. Okay, so first we start off with our limit definition. So we have that f prime of 2 is equal to the limit as h goes to 0 of f of 2 plus h minus f of 2 all divided by h. Then what we'll do is everywhere where we see an x in f of x, we'll put in a 2 plus h, and then subtract off f of x evaluated at x equals 2. And when we do that, we get the limit as h goes to 0 of minus h squared all divided by h. So a rule of thumb when doing these is that you want every term that doesn't have an h in it to cancel out. So if we'd gotten down to this step and we still had a term that had no h in it, that suggests that we've probably done the wrong thing, and we'd want to go back and just make sure that we've done everything correctly. The reason for that is that if you wind up with a term here that doesn't have an h in it, as h goes to 0, the whole thing is going to go off to infinity, which is usually not correct. So just if we had, say, a plus 2 sitting in the numerator, we'd want to go back and just make sure that we haven't multiplied something incorrectly or maybe accidentally flipped a sign. So again, remember that good algebra skills are really important for working with limits. Okay, so then we can factor in h out of our numerator, and we'll get that our numerator is going to be h times minus 1 minus h, and it's all still divided by an h, so we get the limit as h goes to 0 of minus 1 minus h. That's a polynomial in h, so using what we said about continuity, we can just plug in h equals 0 and get that we can get that the limit is minus 1. Okay, so now let's do this again for x equals 3 halves. So we'll do the same kind of thing everywhere where we see an x, we'll first replace it by 3 halves plus h, and then we'll subtract off f of x evaluated at 3 halves. When we do that, we get that our limit as h goes to 0 is minus h squared over h. We can cancel off an h and just get minus h. As h goes to 0, that limit is going to be 0. So what it tells us is that the slope of the tangent line at x equals 3 halves is 0. Okay, and then the last thing that we want to do here is define the derivative function. So what we just found was the derivative at a particular point. If we wanted to go and find the derivative for some particular function at various places, we could do it by finding that limit at the various points, or we could first go and find the derivative function and then go and evaluate that function at the various points. So what we'll do is we'll find the derivative function for minus x times x minus 3, and then we can go and compare it to the answers that we just had, and we'll also go and find a tangent line to f of x at the point, I'll use a equals 7 just for notational clarity. Okay, so the first thing that we'll do is we'll go and look at f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x all divided by h. So we get first f of x evaluated at x plus h, so everywhere where there's an x we'll replace it by x plus h. That'll give us a minus x plus h times the quantity x plus h minus 3, and then we'll subtract off f of x, so subtract off minus x, x minus 3. We can then go and expand everything out and then simplify, and when we do that, we get the limit as h goes to 0 of minus 2xh minus h squared plus 3h all divided by h. So again, in the numerator, we see that everything has an h in it, which is good. Okay, so then we'll factor out an h from everything in the numerator, use that to cancel with the h in the denominator, and get the limit as h goes to 0 of minus 2x minus h plus 3. And that's a polynomial in h, so we evaluated h equals 0, and we get minus 2x plus 3. Immediately from that, we can confirm the answers that we just had. So f prime of 2, we would get minus 2 times 2, which is minus 4 plus 3 for the minus 1 that we just had. And f prime of 3 halves will get minus 2 times 3 halves plus 3, which is clearly 0, and also what we just had. Okay, so then we'll finish off here by giving the tangent line at 7. So we know that f prime is minus 2x plus 3. We can evaluate our derivative function at 7 and get minus 11. And f of 7 we could easily find to be minus 28. So our expression for the tangent line is going to be y equals f prime at 7 times x minus 7 plus f of 7. So then we'll just go and insert what we just had for f of 7 and f prime of 7. And simplifying it down, what we'd wind up with is y equals minus 11x plus 49. Okay, so I think that gives us a good introduction to derivatives, and there will be a worksheet sitting in WILE courses for you to do on this topic. And I will see you all in the next video.